Welcome back, everybody. We're continuing our notes on Chapter 8, Work and Energy, and in particular, kinetic energy. And if you did the last example problem, example 8.5, you kind of saw how kind of a pain it was to go the route of using acceleration to link kinematics to work and energy. Well, this theorem right here, the work-kinetic energy theorem, is going to allow us to bypass that. Because what we're saying is that work, the net work that is done on something, is done because of a change of kinetic energy. Think about it for a second. You have energy in your body. There's potential energy, there's chemical energy, if you're doing work, most likely there's kinetic energy. And as work gets done, you get drained of energy. All right, it's just kind of a natural process. And so work can really be described as a change of kinetic energy. Now, I've been writing this energy as capital Ke right here. But if we kind of back up the scale, we can say that the net work is 1/2 mg, I should say final squared, minus 1/2 mv initial squared. All right, so Ke final. And K, that's different notation here. Sorry about that. This right here should be just initial. Okay, sometimes O stands for original. So the final kinetic energy is 1/2 mv final squared, and the initial kinetic energy is 1/2 mv initial squared. We can say that the change of them is really the work that is being done. We call this the work-kinetic energy theorem. If you just write that, you should be able to write down if you just remember that, you know that this is true, because kinetic energy is 1/2 mv squared, whether it's initial, final, or otherwise. Okay? The work kinetic energy theorem. With this in hand, we should be able to address final velocity, initial velocity, and relate it to work much more easily, because, look, kinetic energy has velocity in it. Velocity final, velocity initial. All right, so what this theorem does is it bypasses all the work that we did on example 5 and puts it into a nice, neater package for us. So let's go ahead and see if we can try that out. Okay, so we have a boy pulling a sled. All right, so here's the sled. I'm gonna let's see, we'll make it black. All right, so here it's just a square on the ground, all right? And he's pulling the sled, presumably with a string, I guess, at 29 degrees above the horizontal, all right? The force right there is 11.0 newtons. 11 newtons at 29 degrees from the horizontal. So that's our theta right there. All right, I'm going to write it on, I'm going to say that it's on the ground is like ice, all right? So it's frictionless, or it's virtually frictionless. All right, well, the mass of the sled, I'm still in blue here. The mass of the sled is going to be, what is that, 6.4 kilograms. 6.4 kilograms, and what we want to find is the work that is done by the boy on the sled, all right? The distance that it moves is 2.0 meters, and the initial velocity, to squeeze that in there, is 0.5 meters per second. All right, so we want to find the work done by the boy. We want to find the final speed of the sled. Okay, those are the two things that we want to find right there. You got it? So, let's go ahead, and I'm going to take this and shrink all this down right here, and hopefully we'll have enough space to do this problem. All right, so let's do that, and I'm going to put that right up in there. Got it. So, all right, so for part 1, or for part A, we want to find the work done by the boy, all right, on the sled. All right, well, we know that work is force, or you might say the net work net work equals net force times distance times the cosine of the angle between them. All right, well, what is the net work that is done on the force? Well, or on the sled. It's done by the buoy, and there's no other net force on it. All the other forces, like for example, gravity force, all right, mg, and our normal force, which we usually draw in black, all right, they're balanced, right? So the only net force is applied by the buoy on the sled. There's not even any friction because it's on a presumably frictionless surface. Okay, that's the net force on the sled, and we do have an angle between them. All right, what is that angle? That's 29 degrees. So our net force is 11.0 newtons plus our distance. How far has it gone? 2.0 meters times a cosine of what's the angle between them? The cosine is 29 degrees. All right, so what's the net work done by the buoy right here? That's 11 times 2 times the cosine of 29. I get 19.2 joules. 19.2 joules of work. All right, let's box it up because that's part A right there. All right, solving for the net work done by the buoy. By the way, I didn't mark this before. I probably should have. Do it in light green. Remember that the distance that it is moving is in that direction right there. So that's where we got the 29 degrees from. All right, it's moving horizontally. The force is being applied upwards, and so that 29 degrees is really our phi, right? Our angle between them. So sorry about that. All right, so we have our net work done on the sled by the buoy. Let's now find the final velocity. Part B, the final velocity of the sled equals, well, we don't know. Okay, well, we do know that net work equals the change in kinetic energy of the sled. And a change in anything is always final minus initial, right? So that's going to be Ke final minus Ke initial. And even those we can write out in more detail. That's 1/2 mv final squared minus 1/2 mv initial squared. All right, well, that equals net work. We should be able to solve then for the final velocity of the system of the sled because we had the work kinetic energy theorem. All right, so let's get everything away from what? Let's get everything away from this right here. All right, so we can say that I'm just going to rearrange things. 1/2 mv final squared equals the net work that is done, which we know already because we solved for it, plus 1/2 mv initial squared. All right. Well, let's solve for v final. V final is we're going to multiply by 2 on top right, and we're going to divide by m. So that's going to be 2 times net work plus 1/2 mv initial squared. And close brackets, and we're going to divide by m right there. All right, now we can't cancel out the m's, right, because there's no m over here, so that has to stay right there. Oh, you know what? I forgot to put my v final. Well, you know what? I was going to make the v final squared and then rewrite that, but instead, how do we get rid of all this stuff and get rid of the squared? We take the square root, right? So that is our working equation now for the final velocity of the sled. And it's a lot neater than in the last example where we had to equate everything to acceleration and so on and so forth. This takes us right there. So let's just plug and chug and find out what we get. So the square root of 2 times, what's the net work? 19.2 joules. I don't want to close brackets yet. Plus 1/2. In fact, I'm going to say 0.5 because it's going to be easier to type in 0.5 into a calculator. 0.5 times, what's the mass of the sled? That's 6.4 times, I'm not going to put my units in just because I'm going to run out of space, times what's our V initial squared? That's 0.5 meters per second. I guess I can squeeze that in. Squared, right? Don't forget to square that second 0.5 right there. All that over the mass of the sled, which is 6.4 kilograms. All right? Got it. So I'm going to go ahead and key that into my calculator and see what I get, and hopefully you'll do the same thing, and we'll agree on what we get for the final velocity right here. So I get a final velocity of 1.77 meters per second. There we have it. And again, if you compare this to our last example where we had to go through this whole rigmarole of comparing work to force and then force to acceleration and acceleration to final initial and final velocity, this work kinetic energy theorem is a heck of a lot easier. So keep that in your hip pocket, the fact that work, the net work is really a result of our change in kinetic energy. That's really what saved us all that effort right here on this one. Of course, change being final minus initial. So there you have it. There is our work kinetic energy theorem at work, no pun intended, and that's example 8.6. So please see me if you are confused on any of this, and I'll be glad to clear that up for you. Thanks a lot, and I'll see you on the next one.